Okay, so we're looking at what we can do after week 1, and we're going to do a self-assessment, and we're going to check and see if we can do these skills that are necessary as we're going forward to study organic chemistry. So can I draw Lewis structures for polyatomic ions and molecules with 3 or more atoms? Can I use electronegativity, identify it for a given atom, and then use it to assign polarity? Can I push arrows to form resonance structures? And then can I calculate formal charge and be able to rank resonance structures based on the distribution of charge? Can I use the valence shell electron repulsion theory to predict my molecular geometry? And then can I draw sp, sp2, and then sp3 hybridized molecules and be able to identify the sigma and the pi bonds? And last but not least, can I identify and draw functional groups? If you can do that, fantastic. If not, this might be a really great opportunity to connect. Just wanted to give a heads up. So you're going to take a quiz on Thursday before the end of next week. So not this week, but next week. You can see me during the time that works for you. You're going to review and correct your amino acids quiz with me, and then you get 3 additional points. So this is an opportunity for you for either your Tuesday or your Thursday quiz to touch base and make corrections. We're going to talk about functional groups today in a little bit more depth, but I want you to be thinking about how you can start practicing to recognize these functional groups. So I know that for some of you, these are molecule components that you've already been exposed to, but it's worth thinking about how you're going to study these, whether that's flashcards or drawing them out or finding a whiteboard to practice on, or figuring out some way to do a Quizlet online. Those are all great options. Let's just find one that works for you. These are all of the functional groups that you are going to be responsible for. You've got a sheet from me in class that details these further. We're just going to do a quick review where we talk about the main players. So alkanes, alkenes, alkynes, benzene rings. Those are all of the carbon-hydrogen-only components in functional groups. Then amines, alcohols, ethers, alkyl halides, thiols, aldehydes, ketones, esters, carboxylic acids, amides, nitriles, epoxides, disulfides, imines, acid chlorides, anhydrides, nitro compounds, and sulfides. Notice I've broken them apart into kind of main players and supporting actors. I thought this designation was really useful because you've probably seen the main players at some point. It's the supporting actors that maybe you're not as familiar with. By the end of the semester, you're going to feel comfortable with all of them. Arrhenius acids and bases is the next topic that we're going to explore. So in 1884, Arrhenius proposed definitions for acids and bases. So an acid would be a substance that dissolves in water and produces hydronium ions, whereas a base is a substance that dissolves in water to produce hydroxide ions. So these definitions of an acid and a base are slight modifications of the originals, but we know that instead of producing an H+, a water molecule is always going to react to give a hydronium. So let's take a look at an example. If we're looking at HCl, and we know that it dissolves in water and it's going to react, we want to be able to think about how we can draw arrows to show the change in the position of the electron pairs, or we want to be able to practice drawing a mechanism. So the lone pair on the oxygen is the most electronegative of the water molecule, and that's going to react with the hydrogen of the HCl because it's the least electronegative. So that's that delta negative reacting with a delta positive that we talked about in class. And when that happens, we know that hydrogen can only have one bond because it can only have 2 electrons. So that means that the bond between H and Cl has to break. So I want you to take a moment and for HBr, see if you can draw that mechanism. So think about the example from previously, and if you need to, pause so you have a little bit more time. Or you can always go back and check. With bases, the situation is slightly different. So many bases are metal hydroxides, such as potassium hydroxide, sodium hydroxide, magnesium hydroxide, and calcium hydroxide. These are compounds that are ionic solids, so they look like salts. And when they dissolve in water, their ions separate. Because they're ionic compounds or salts, they're going to behave in a specific way where if you were to put them in solution, you would see complete separation between the sodium positive and the hydroxide. Other bases, for example, though, are not hydroxides, and these bases are going to produce OH minus by reacting with water molecules. A great example is ammonia. So when ammonia reacts with water, it produces ammonium and hydroxide. See if you can draw a reaction mechanism for that process. So for NH3 reacting with water to form hydronium and the hydroxide, take a moment and draw the mechanism. So we use curved arrows to show the transfer. I have a lone pair on my ammonia. That's, again, my nitrogen, which is my most electronegative atom out of this molecule. And that's going to react with the hydrogen, which is the least electronegative atom on this entire molecule. And that's going to form NH4 plus and OH minus. So if you have an areneous acid, that's going to increase the concentration of hydrogen ions when I place it in water. So the strength of this acid really depends upon how many of these hydrogen ions are produced. And you can actually see that this is going to be a dissociation. And it's going to require an equilibrium equation. So write the dissociation reaction for HNO3. Likewise, an areneous base is a substance that increases the concentration of hydroxide ions, OH minus, when it dissolves in water. Go ahead and write the equilibrium dissociation reaction for the base lithium hydroxide. Practice is always something that is helpful, so I want you to take a moment, think about your definitions of areneous acids and bases, and then for the following reactions, go ahead and draw the reaction components. So the starting material is given. I want you to tell me the products. But then I also want you to think about drawing a mechanism. That should help you kind of cement your working knowledge. So Bronsted-Lowry acids and bases are slightly different definitions. I know, they look really grumpy there, but actually they were brilliant men who made a significant contribution to our understanding of the behavior of acids and bases. So their definition is that an acid is a proton donor and a base is a proton acceptor. And so when we think about conjugate bases and conjugate acids, a conjugate base is what forms when an acid gives up a proton. What's left forms a base. A conjugate acid is what is formed when a base accepts a proton. So when we're looking at an acid-base reaction, it's really helpful for us to think of that as a proton transfer reaction. And any conjugate acid-base pair, so any pair of molecules or ions that can be interconverted by the transfer of a proton, would be a conjugate acid-base pair. So we're going to illustrate these relationships by the reaction of hydrogen chloride with water. You're going to be like, we saw that example before. You're right. Now we're going to think about it in a slightly different way. So take a moment. Again, think about how you would draw the mechanism for this reaction. Identify what is transferring the proton. That's going to be your acid. What is receiving the proton? That's going to be your base. And then what has lost the proton? That's going to be your conjugate base. And what has gained the proton? That's going to be your conjugate acid. This shows you how we would identify conjugate acid-base pairs. So notice the HCl gives up the H, so the Cl minus becomes the conjugate base. The water receives the proton or takes the proton, depending upon how you want to designate that, and it becomes the conjugate acid. So let's do that for something that's not water. So for example, we're going to look at acetic acid and ammonia, which will form the acetate ion and the ammonium ion. Go ahead and assign acid, base, conjugate base, and conjugate acid. And if you want, draw a mechanism. So we use curved arrows to show the flow of electrons that occur in the transfer of a proton from acetic acid to ammonia. So for example, this electron pair takes the electrons from the bond between oxygen and hydrogen and puts those electrons onto the oxygen, forming a negative charge. That's how we get the acetate ion, our conjugate base. And it's actually ammonia, the base, where the lone pair takes that hydrogen. So notice the electrons from the bond go onto the oxygen, and the electrons from the nitrogen take the hydrogen. We could do any combination. In fact, one of the best ways to practice Bronsted-Lowry acid-base pairs is to choose two and determine what the relationship or the interaction is between them. It's useful for us to think about strong and weak acids and bases. So a strong acid is one that reacts completely or almost completely with water to form hydronium ions, whereas a strong base is one that reacts completely or almost completely with water to form hydroxide ions. Weak acids are substances that only partially dissociate in water to produce hydronium ions. So for example, acetic acid is a weak acid. In water, only 4 out of every 1,000 molecules of acetic acid are converted to acetate ions. Likewise, a weak base is a substance that only partially dissociates in water to produce hydroxide ions. Ammonia, for example, is a weak base. So if I know that acetic acid is incompletely ionized in aqueous solution, then I can actually write an equation for the ionization of the weak acid, where I write an equilibrium expression where I have my products, my hydronium and my A- over my HA. And I can exclude water from this term because water is a pure liquid. So if I'm going to determine the position of equilibrium in an acid-base reaction, I have to identify what's the acid, one on the left, one on the right, so an acid on either side of my arrow, and then I have to use the information in table 2.2 to determine which is the stronger acid and which is the weaker acid. So if we think about this, we remember that the strong acid gives the weaker conjugate base, and the weaker acid gives the stronger conjugate base. And so I'm always going to go from strong to weak. So when I'm drawing my arrows, I know that equilibrium lies on the side of the weaker acid and the weaker base. So let's take a moment and practice that. So I've got my acetic acid and my ammonia, and I'm going to think about pKa. So if you recall, right, the smaller the number of pKa, the stronger the acid. So in this case, I'm going to go from acetic acid and ammonia to the acetate and the ammonium ion. So I'm going to go ahead and label all of my pairs. This we've already done. Right? And then I know that equilibrium goes from the left to the right. So my predominant arrow goes in this direction. It's going to help you to go back and do a quick review of your functional groups just to make sense of what you know. And you're going to notice now that we have a pKa table that you will always have access to. So whenever you are solving equilibrium reactions, you're going to use a pKa table to be able to determine which is the strong acid and which is the weaker acid. Next time, we're going to talk about how a chemist saved 2 Nobel Prizes from the Nazis using 2 strong acids. Thanks again for your time. Hope you have a great day.